गुड आफ्टरनून बच्चों। आज हम टॉपिक्स जो लिया है दैट इज आइडियल एंड नॉन आइडियल सॉल्यूशंस। जैसे हमने पहले पढ़ चुके हैं आइडियल गैसेज के बारे में। देयर आर सम गैसेज विच बिहेव लाइक आइडियल गैस एंड सम बिहेव एज नॉन आइडियल गैस। ओके, आइडियल गैस किसको कहते थे हम? विच फॉलोज गैस लॉ, आइडियल गैस लॉ लाइक योर बॉयल्स लॉ, then your Charles law and Avogadro's law. What is Boyle's law? That is volume is proportional to 1 upon pressure when N and T are constant. That is number of moles and temperature is constant. Charles law was volume is proportional to temperature when number of moles and gas pressure is constant. Similarly, Avogadro's law is volume is proportional to number of moles when pressure and temperature are constant. So the gases which obey these laws, those were called ideal gases. Okay, we can combine this as V is proportional to T into N upon P, or we can write PV is proportional to NT, or we can write PV equal to nRT, where N is the, with this R is the universal gas constant. ये आइडियल गैसेज के लिए है। अगर हम नॉन आइडियल गैसेज की बात करें then this equation will become PV equal to ZnRT, where Z is the compressibility factor. If Z was greater than 1, we say that this gas is showing positive deviation from the ideal behavior. If Z is less than 1, we said that it is showing negative deviation from the ideality. Similar way, we will study the ideal and non-ideal solutions. Suppose we have two volatile liquids. Okay, one is A in this container and there is another volatile liquid B in another container. Okay, and suppose this is exerting a vapor pressure of PA naught and this is exerting a vapor pressure of PB naught. अगर हम इन दोनों सॉल्यूशंस को मिक्स कर देते हैं एक दूसरे कंटेनर में, then it will have the molecules of A and B both. And it will exert some pressure that is given by Raoult's law, that is P total, that is partial pressure of A plus partial pressure of B. And what was PA as per Raoult's law? That is PA naught into XA. And what is PB? That is PB naught into XB. So this was as per the Raoult's law. अब ये अगर सॉल्यूशन आइडियल है तो इट विल फॉलो द राउट्स लॉ। दैट मीन्स अगर हम इस सॉल्यूशन का प्रेशर मेजर करें देन ऑब्जर्व प्रेशर जो होगा हमारा दैट विल बी इक्वल टू ऑब्जर्व प्रेशर। अगर मान लो इसका प्रेशर मेजर करें मैनोमीटर से तो जो प्रेशर आएगा इफ इट इज इक्वल टू PA नोट XA प्लस PB नोट XB, then we will say that this solution is ideal solution. Okay, so that means it is following the Raoult's law. अभी हम डिस्कस करेंगे कि आइडियल सॉल्यूशन होने के लिए क्या कंडीशन नेसेसरी है, which solutions we can call as ideal solutions. So as a definition we can say that those solutions which follow Raoult's law at all concentrations and temperatures, they can be called as ideal solutions. So this is the definition for ideal solutions. यानी अगर हम दो लिक्विड्स ए और बी को मिक्स करें तो जो उनका सॉल्यूशन बनेगा, दैट वेपर प्रेशर एक्सर्टेड बाय दैट सॉल्यूशन, दैट शुड बिकम इक्वल टू द वेपर प्रेशर दैट इज कैलकुलेटेड एज पर द राउल्ट्स लॉ, देन इट विल बी कॉल्ड आइडियल सॉल्यूशन. अब आइडियल सॉल्यूशन होने के लिए क्या क्या कंडीशंस होनी चाहिए? Suppose again I take that example. Suppose there is a container having liquid A. This is your liquid A, and this is having liquid B. अब जब हम इनको मिक्स कर देंगे तो we will get a mixture having molecules of A and B. अब होगा क्या, इसके अंदर जब ये प्योर लिक्विड A था, दिस इंटरेक्शंस वर बिटवीन द मॉलिक्यूल्स ऑफ A एंड A, so it was having A interactions. What is intermolecular force of attraction? That is the van der Waals forces of attraction between A molecules of A and A. Similarly, this liquid B will have BB molecular interactions. Okay. When we mix the two solutions, the interactions of AA will be broken, the interactions of BB will be broken, and new interactions of AB will be formed. यानी जब हम लिक्विड A सेपरेट था तो इसके अंदर molecules of A and A were having some interactions, and similarly B and B molecules were having some interactions. But when we mix the two liquids, this mixture will have the molecules of A and B both. So now the interactions will be between A and B. Okay. So if these interactions are almost same, that means AA interactions is equal to AA is equal to BB interactions is equal to AB interactions. अगर ये interactions almost same है, then we will say that these liquids A and B form an ideal solution. Okay. Why it is so? Because if we mix the two liquids, then final volume of this mixture, if we say V final, that will be equal to, say, this is volume V1, this is volume V2. Then V final will be equal to V1 plus V2. Okay, and this delta will be 0. That means V final equal to summation of the two. Okay, so we can say that delta V mixing is 0 in case of ideal solutions, because the interactions are almost identical. So the volume will neither increase nor decrease. So what are the conditions that this ideal solution will satisfy? Number one is delta V mixing will be 0. That means there is no change in volume of the solution after mixing the two liquids. Number two, delta H mixing will be 0. That means there is no enthalpy change on mixing of the two liquids. So it is neither exothermic nor endothermic. Number three, we can say that the vapor pressure exerted by the solution, vapor pressure of solution is same as that predicted by Raoult's law. That means it obeys Raoult's law. So its vapor pressure is observed vapor pressure. What we actually see after measurement is found to be equal to, say, PA naught XA plus PB naught XB. So these three conditions it has to satisfy. And what is the main condition? The molecular interactions, that is intermolecular forces of attraction between the molecules of A and that between B and B should be almost same as that between molecules of A and B. Okay, so that is the prior condition. If that condition is satisfied, then all these three will be satisfied. Then we say that this is an ideal solution. Okay. Now we will ask that there is another two conditions, that is delta S mixing. It will be always greater than 0, whether it is ideal solution or it is non-ideal solution. That is, the entropy change on mixing will be always positive, because when we mix the two liquids, the number of molecules will increase, so the randomness will increase, so the entropy change will be positive. And similarly, your delta G mixing, that is the Gibbs free energy change on mixing, will be less than 0, because this process is spontaneous. So these are the conditions that are to be satisfied by the ideal solution, and these two conditions they hold for both ideal as well as non-ideal. Okay. So now we take some examples of ideal solutions. After that we will take the non-ideal solutions. So let us take some examples of ideal solutions. First we have to see that both the solutions, both the liquids should be of identical nature. Say polar, if one liquid is polar, then other should also be polar. Okay. If one is non-polar, then other should also be non-polar. Why so? Because the intermolecular forces of attraction need to be identical. Then only this solution will behave as ideal solution. So if we take one polar and one non-polar, then these molecular interactions will be significantly different and the solution formed will not be an ideal solution. So let us take some example. Say I take the example of, say, methanol plus ethanol. So they will form an ideal solution because both are having hydrogen bonding of the same extent and both are polar molecules. Okay, and suppose I take two non-polar molecules, then also they will be, like say I take benzene plus toluene. So both are non-polar, so they will make ideal solution. And the difference in their molecular masses is also not much high because they are just adjacent in a homologous series, like your methanol and ethanol. If I take, say, methanol plus propanol, that is C3H7OH, then they will not form ideal solution, they will form non-ideal solution. Why? Because the molecular interactions will be significantly different because of the size change is very high. Means the molecular mass of propanol is significantly higher than methanol. So the van der Waals forces between the two will be significantly different. So they will not form an ideal solution. Similarly, say I take benzene plus, say, xylene. Instead of toluene, I take xylene. Then also it will not form ideal solution. It will form non-ideal solution. Okay. And these are the ideal solution. This is also ideal solution. If I take, say, N-hexane plus N-heptane, that will also form ideal solution. Okay, say I take C2H5Cl plus C2H5Br, that will also form ideal solution because they are chlorine and bromine, both are adjacent to each other in the group. So with this we know that which solutions can behave as ideal solutions and which can behave as non-ideal solutions. Now we take how this ideal solutions can be represented graphically. Okay, suppose I draw a curve like this. Okay, here say it is a pure B. If it is pure B, then XA will be 0 at this point. Here XA will be 1 because it is pure A. Now if I draw this vapor pressure curve, partial pressure, so PA is equal to PA naught XA. So it is like your y equal to mx line, where PA naught is the slope of this line, so it will be like this, and this point will represent PA naught, that is vapor pressure of pure A, because here it is pure A. Similarly, if I draw another line for B, then PB will be equal to PB naught into XB. So this will come like this. Okay, and here it will be PB naught. And if I join these two points, this line will represent P total, that is nothing but PA naught XA plus PB naught XB. So by this curve, by these lines, we can represent the ideal solution. Okay. And with this we see that B is more volatile than A because vapor pressure of B is higher than A. Now I take the example, so I take some non-ideal solutions, and what are the criteria for non-ideal solutions. First, I will divide the non-ideal solutions into two categories. That is, one is the showing positive deviation from the Raoult's law, and other will show negative deviation from. So this side I will write positive deviation, and this side we will write negative deviation from Raoult's law. Now see, what are the various conditions to show positive deviation. For showing positive deviation, your delta V mixing has to be greater than 0. Delta H mixing, that is enthalpy change on mixing, has to be greater than 0. Your observed pressure P total has to be greater than that predicted by Raoult's law, that is PA naught XA plus PB naught XB. So these are the three conditions that are to be satisfied by solutions showing positive deviation. And for negative deviation, it will be opposite, that is delta V mixing will be less than 0, then delta H mixing will be less than 0. That means the process will be exothermic. Here the process is endothermic, and then our vapor pressure of the solution as measured, that is observed vapor pressure will be found less than that predicted by the Raoult's law, that is PA naught XA plus PB naught XA. Okay. Now why these conditions have come? The basic thing which has happened for positive deviation is the AB interactions. If I write AB interactions, they are weaker than AA and BB. Okay, because the AB interactions are weaker, that is why the solution, from the solution, the molecules have a greater tendency to escape to the vapor state. So the vapor pressure exerted by the solution is higher than that for the ideal solution. In this case, it will be opposite. In this negative deviations, this AB interactions will be stronger than AA or BB interactions. That means AB interactions are greater than AA or BB interactions. So this is the main reason for all these deviations. Okay. Now you see why delta H mixing is greater than 0 for this solution having AB interactions weaker. Because when AB interactions are made, AA bond is broken, then some heat is absorbed, BB bond is broken, then some heat is absorbed, and the AB interaction, some heat is evolved. If that heat evolved is less than the heat absorbed, then the net heat will be absorbed, so delta H mixing will be greater than 0, and this is opposite for this. Now we will take some examples, with that it will be more clear. Let us take some examples for solutions showing positive deviation and those showing negative deviations. First we take the solution showing negative deviation. Suppose I take a solution with say HNO3, nitric acid plus water. It will show negative deviation. As we know, whenever we mix some acid in water, it is an exothermic process. So delta H mixing will be less than 0. So it is showing negative deviation. Similarly, if I take say chloroform, that is CHCl3 plus acetone, that will show negative deviation. Then I take say phenol plus aniline. What is phenol? That is C6H5OH plus aniline. What is aniline? C6H5NH2. So they will show negative deviation. Why this chloroform plus acetone is showing negative deviation? Because they will form hydrogen bonding. This is a typical example of a compound which shows hydrogen bonding even when hydrogen is not connected with fluorine, oxygen or nitrogen. Normally hydrogen bonding is shown by compounds where hydrogen is attached with either of fluorine, oxygen or nitrogen. But in this case, hydrogen is not attached with any of these, even then it is showing hydrogen bonding. I will show how it is showing hydrogen bonding. Okay, first, and why phenol plus aniline is showing negative deviation? Because the hydrogen bonding extent will be more in case of the mixture as compared to the individual hydrogen bonding shown by phenol and aniline. So even though phenol has hydrogen bonding, aniline also has hydrogen bonding, but the hydrogen bonding extent in the mixture of phenol plus aniline is more as compared to the individual hydrogen bonding. That is why it shows negative deviation. Okay. Now let us take some examples of solutions showing positive deviation. Here the hydrogen bonding is broken, then it will show positive deviation. Suppose I have a mixture of say CH3OH, that is methanol, plus I take say acetone. Now what will happen? This will show negative deviation because acetone will try to weaken the hydrogen bonding of methanol. Suppose I take example of CH3OH plus CCl4, carbon tetrachloride. This will also weaken the hydrogen bonding of methanol. Now let us take some more examples. Say I take the example of carbon disulfide plus acetone. It will show negative positive deviation. Why? Because this is a non-polar molecule. CH2 is non-polar. CH2 is like this linear molecule. So it is a non-polar molecule, and acetone is polar molecule because it is like CH3 CO CH3. So it is a polar molecule. Because oxygen is more electronegative, so it is a polar molecule. So we can take various examples like this. Suppose I take water plus I take say ethanol, that will also show positive deviation. Why positive? Because water has stronger hydrogen bonding as compared to ethanol. So when ethanol is mixed with water, it will weaken the intermolecular hydrogen bonding of water. So it will have positive deviation. It will show positive deviation. We can take various examples. We can take say benzene plus water. Benzene will weaken the intermolecular hydrogen bonding of water, so it will show positive deviation. Now we will show how this negative and positive deviation with some examples, why they are showing positive and negative deviation. Let us take one example of this. I told this chloroform plus acetone. This is a very important example. So how it will show? It will be like this: CH single bond Cl, 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 CH, Cl3, and acetone will be like CH3, CO, CH3. Okay. Now this chlorine being more electronegative, it will pull the electrons from carbon, and this carbon will pull the electrons from this hydrogen. So ultimately this hydrogen will have delta plus, and this oxygen is delta minus, and it has also the lone pairs. Okay, so this hydrogen which is electron deficient will make hydrogen bonding with this oxygen because it is having two lone pairs. So that is how this hydrogen bonding occurs between chloroform and acetone, even though the carbon is not connected with any of the fluorine, oxygen and nitrogen. Okay, so this is a special example. Now why this phenol and aniline? So this is like your phenol. Say this is your phenol, and this is the aniline. Now this oxygen being having lone pairs, and this nitrogen is electronegative, so it will have delta minus, and this will have delta plus. So these two lone pairs on oxygen, so this will form hydrogen bonding with aniline, and similarly this hydrogen will again form hydrogen bonding with another molecule of aniline, and the extent of hydrogen bonding between the two is more than that between individual molecules of aniline or phenol. That is why they show negative deviation from the ideal solution, that is from the Raoult's law. Now how we can show graphically this non-ideal solution? First we had shown the ideal solution. Now let us show the solution with positive deviation. Suppose I want to show the positive deviation. So this is again XB equal to 1 and here XA equal to 1, that is pure A, and here it is pure B, means here XA equal to 0. So if I make this it were ideal solution, that it will be like this. So this will be PA naught, and say ideal solution if it were, then it would have been, it will be PB. But as it is showing positive deviation, so the partial vapor pressure of A in the solution will not be equal to PA naught XA, rather it will be greater than PA naught XA. Similarly, partial vapor pressure of B in the solution will be higher than that predicted by the Raoult's law, that is PB naught XB. So this curve, this was the total if it were ideal. Now in case of this positive deviation, this will be like this, and similarly this will be higher than pure, this higher than that predicted by the Raoult's law, and this total vapor pressure will also be higher than that predicted by the Raoult's law. So this is the solution, non-ideal solution showing positive deviation from the Raoult's law, and the total pressure, if I say observed total pressure, that will be found greater than PA naught XA plus PB naught XB. So this is the solution showing positive deviation. Similarly, if I can draw the lines for the solution showing negative deviation, and that will be just opposite to what we have shown just now. Now there is a term called azeotropic solution, azeotropic mixture, azeotropic mixtures. These non-ideal solutions which show positive deviation or which show negative deviation from the Raoult's law, they form azeotropic mixtures at a particular composition. Okay, so solutions showing positive deviations, they will form azeotropes, that is called minimum boiling azeotrope. They are called minimum boiling. Why we say minimum boiling azeotrope? Because the boiling point of the mixture at that composition will be lower than that of individual pure liquids. And similarly, the solutions which show negative deviations, they will form maximum boiling azeotrope. That means their boiling point at that particular concentration will be higher than individual boiling points of the two components. Okay, now let us take one example for each. Let us take for negative deviation. Suppose I have a mixture of nitric acid plus water. We know that this shows negative deviation. So it will form an azeotrope which will be maximum boiling azeotrope, and this is at a composition of say 68%. When this concentration of nitric acid reaches 68% by mass, that is HNO3 concentration is 68% by mass, then it will form the maximum boiling azeotrope. That means the boiling point of the mixture will be higher than that of water as well as nitric acid, and it is found to be around 120.5 degrees Celsius for this mixture at azeotropic condition of 68% by mass. So what is meant by this azeotropic mixture? That means whenever we fractionally distillate this solution, we cannot separate this solution into its individual components more than 68% nitric acid by mass. That means we can achieve nitric acid up to 68% concentration by the fractional distillation. We cannot achieve more than 68% nitric acid by fractional distillation because it forms an azeotrope at 68% concentration. Means it will called a constant boiling mixture. Means the liquid phase and the vapor phase concentration will become identical. Normally when we do the fractional distillation, the vapor phase will have higher composition in more volatile component and less in less volatile component. But in case at azeotropic condition, this will have identical composition in liquid and vapor. So separation by fractional distillation is not possible after achieving the azeotropic composition. And similarly, we take the example of say solution which show minimum boiling azeotrope. The example is ethanol plus water. Ethanol plus water. We get ethanol plus water solution from fermentation industry, where we want to separate this ethanol. We want to purify the ethanol to maximum concentration, but as soon as the ethanol composition reached 95%, 95.6% ethanol by mass, then it will form an azeotrope. Azeotrope. That means further separation of ethanol from water is not possible. That means we cannot purify the ethanol from ethanol water mixture beyond 95.6% ethanol by mass, because at that composition it will form a minimum boiling azeotrope. That means the boiling point of the mixture will be lower than that of individual components, and the vapor phase and liquid phase composition will become identical, so no further separation will be possible. So this is how we conclude our session with this, and we will take next session on some other topic. Till then, goodbye. Thank you.